everyone, I am Shari Oladive.
And I am Maria Bettina Gabriel F. Ronda. This video presentation entails our exposition of Mr. Mondal, Banerjee, and Roy's first-order linear homogeneous ordinary differential equation in fuzzy environment.
For the abstract, in this paper, the researchers describe first-order linear homogeneous ordinary differential equation in fuzzy environment. The concept of fuzzy number, its operation with its membership function, and special type was presented.
Here, fuzzy numbers were taken as generalized triangular fuzzy number. Fuzzy ordinary differential equation was distinguished from ordinary differential equation, and its strong solution was shown. Its solution procedure was discussed in 3 cases. Moreover, biomathematical decay and growth models were numerically illustrated to show its applications.
The retrieved literature and studies that the researchers gathered influenced and improved their thoughts concerning the first-order linear homogeneous ordinary differential equation in fuzzy environment. In this regard, the researchers seek to answer the following questions. First, what is a fuzzy number? Second, what is a generalized triangular fuzzy number? Third, what is a fuzzy ordinary differential equation? Fourth, what is the strong solution of FOD? Fifth, how is the solution of FOD in fuzzy environment described in the following cases? Only the initial condition is a generalized fuzzy number. Only the constant is a generalized fuzzy number, and both the initial condition and the constant are generalized fuzzy numbers. And the last one, how is FOD in fuzzy environment applied in growth and decay model?
For the significance of the study, this exposition focuses in describing FOD in a fuzzy environment. This will provide consistency and certainty to overcome existing uncertainties and lack of precision in the solutions of differential equations. It is valuable to observe these properties since differential equations play a significant role in terms of biology, engineering, physics, and other fields of science. Also, teachers, students, and researchers will benefit from the elucidation of the topic. With this, individuals with interest in math may refer to it for educational purposes. By having a consistent and certain solution in differential equation, individuals may perhaps apply this concept in providing math models in different real-life applications of differential equations.
The concepts from set theory, calculus, and differential equations were used in this study. Definitions, theorems, proofs, and examples herein were stated for the better understanding of the reader. Here is the list of notations used throughout the paper. For the first statement of the problem, fuzzy numbers are appraised calculations assumed by experts and acknowledged by decision makers when obtaining more accurate value is impossible. Actual problems frequently involve many quantities that are ideals of erroneous information concerning numerical values. For this reason, we use words like around in such cases. An example of this is when we measure the height of an individual. What we acquire is a numerical value with a level of imprecision. This imprecision may be triggered by the measuring instrument, by the persons who took the measurements, by the person who was measured, and for various other reasons. In the end, an accurate value h, which is an element of real number, is preferred to indicate the height of the person. However, it would be more prudent to say that the height is around or approximately h. In many respects, fuzzy numbers depict the physical world realistically than single-valued numbers. We represent the expression around h arithmetically by a fuzzy subset tilde of a, whose domain of the membership function mu sub tilde of a of x is a set of all real numbers.
So basically, a fuzzy number is an extension of a regular number in the sense that it does not refer to one single value, but rather to a connected set of possible values, where each possible value has its own weight between 0 and 1.
The illustration shows a fuzzy number with fuzzy interval a sub 1 and a sub 3 in the real number r. Generally, it is represented by two endpoints, a sub 1 and a sub 3, and a peak point, a sub 2, as a sub 1, a sub 2, and a sub 3. We can see that every element a sub 1, a sub 2, and a sub 3 has its membership.
Second statement of the problem, a generalized fuzzy number is called generalized triangular fuzzy number if it is defined by tilde a is equal to the interval a sub 1, a sub 2, a sub 3 omega. Its membership function is given by this piecewise or in this form. For the second statement of the problem, here is a presentation of generalized triangular fuzzy number. For the third statement of the problem, fuzzy ordinary differential equation. Many phenomena in engineering and sciences can be expressed by equations which involve the rates of exchange of quantities such as position, temperature, and mass that describe the state of phenomena. The state of system is characterized by state variables which give an instantaneous description of the system. The rates of change are derivatives with respect to time, and equations involving derivatives are called differential equations. The differential equations are said to model the phenomenon or process with which they are associated in the following sense. Given an initial state, unique time descriptions of the state variables can be found which solve the differential equations and take on the initial state at the initial time. Consider the first-order linear homogeneous ordinary differential equation. Derivative of x with respect to t is equal to kx, with initial condition x of t sub 0 is equal to x sub 0. Since there are various complications arising due to the difficulties to distinguish events with precision in demonstrating occurrence, fuzzy environment is used to describe this vagueness. Full hold becomes fold if any one of the following three cases hold. First, type 1. Only x sub 0 is a generalized fuzzy number. Type 2, where only k is a generalized fuzzy number. Type 3, where both x sub 0 and k are generalized fuzzy numbers.
For SOP4, consider the full hold given in SOP3 with initial condition x of t sub 0 equals x sub 0. Here, the initial condition or coefficient be generalized fuzzy number. We let the solution of fold be tilde of x of t and its alpha cut be x of t alpha is equal to the interval x sub 1 t alpha and x sub 2 t alpha. Then the solution of the fold tilde of x of t is called strong solution if it satisfies the following three cases. First, x sub 1 of t alpha is an increasing function, that is, the partial derivative of x sub 1 t alpha with respect to a is greater than 0. Second, x sub 2 t alpha is a decreasing function, that is, partial derivative of x sub 2 t alpha with respect to a is less than 0. The third one, x sub 1 of t omega is equal to x sub 2 of t omega for all a element of the interval 0 omega where omega is greater than 0 but less than or equal to 1. Otherwise, tilde of x of t is called weak solution. For the statement of the problem number 5, how is the solution of full hold in fuzzy environment described in the following cases? Only x sub 0 is a generalized fuzzy number, only k is a generalized fuzzy number, and both x sub 0 and k are generalized fuzzy numbers. Consider the initial value problem given in SOP3 with fuzzy initial condition. Let its alpha cut the quantity of tilde of gamma sub 0 sub equals the interval gamma sub 1 plus alpha L sub gamma sub 0 over omega and gamma sub 3 minus alpha R sub gamma sub 0 over omega for all alpha element of the interval 0
omega, where omega is greater than 0 but less than or equal to 1.
Here we solve the given problem for k greater than 0 and k less than 0, respectively. When k is greater than 0, fold becomes fold. Hence, the solution is equal to gamma sub 1 plus alpha L sub gamma sub 0 over omega times e raised to k times the quantity of t minus t sub 0 and gamma sub 3 minus alpha r sub gamma sub 0 over omega times the quantity of e raised to k times the quantity of t minus t sub 0. When k is less than 0, let k is equal to negative m, where m is a positive real number. So the general solution is equal to 1/2 times the quantity of gamma sub 1 plus gamma sub 3 plus alpha over omega times the quantity of L sub gamma sub 0 minus R sub gamma sub 0 times e raised to negative m times the quantity of t minus t sub 0 plus 1/2 times the quantity of alpha over omega minus 1 times the quantity of L sub gamma sub 0 plus R sub gamma sub 0 times e raised to m raised times the quantity of t minus t sub 0, 1/2 times the quantity of gamma sub 1 plus gamma sub 3 plus alpha over omega times the quantity of L sub gamma sub 0 minus R sub gamma sub 0 times e raised to negative m times the quantity of t minus t sub 0 minus 1/2 times the quantity of alpha over omega minus 1 times the quantity of L sub gamma sub 0 plus R sub gamma sub 0 times e raised to m times t minus t sub 0. Since we have shown that the solution of type 1 satisfies the condition mentioned in SOP number 4, it follows that 1/2 times the quantity of gamma sub 1 plus gamma sub 3 times e raised to negative m times the quantity of t minus t sub 0 plus 1/2 times the quantity of alpha over omega minus 1 times the quantity of L sub gamma sub 0 plus R sub gamma sub 0 times e raised to m times the quantity of t minus t sub 0 and 1/2 times the quantity of gamma sub 1 plus gamma sub 3 times e raised to negative m times the quantity of t minus t sub 0 minus 1/2 times the quantity of alpha over omega minus 1 times the quantity of S sub gamma sub 0 plus R sub gamma sub 0 times e raised to m times the quantity of t minus t sub 0 is the alpha cut of the strong solution of the fold given in SOP number 3. For solution procedure of type 2, consider the initial value problem derivative of x with respect to t is equal to tilde of k x with initial condition x of t sub 0 equals gamma, where tilde of k is equal to beta sub 1, beta sub 2, and beta sub 3 lambda. Here we also solve the given problem for tilde of k greater than 0 and tilde of k less than 0 respectively. When tilde of k is greater than 0, the desired solution is gamma times e raised to beta sub 1 plus alpha L sub k over lambda times the quantity of t minus t sub 0 and gamma times e raised to beta sub 3 minus alpha R sub k over lambda times t minus t sub 0. When tilde of k is less than 0, the general solution is a generalized fuzzy number with alpha cut given in this equation. For solution procedure of type 3, we consider the initial value problem in type 2 with fuzzy initial condition and fuzzy constant. So let tilde of k of t be the solution of fold. In addition, we assume that x of t alpha is equal to x sub 1 of t alpha, x sub 2 t alpha be the alpha cut of the solution. Also, we let tilde of k sub alpha equals beta sub 1 plus alpha L sub k over lambda and beta sub 3 minus alpha R sub k over lambda for all alpha element of the interval 0 and lambda, where lambda is greater than 0 but less than or equal to 1, and tilde of gamma sub 0 sub alpha is equal to gamma sub 1 plus alpha S sub gamma sub 0 over omega plus gamma sub 3 minus alpha R sub gamma sub 0 over omega for all alpha element of 0 omega, where omega is greater than 0 but less than or equal to 1. So we let eta equals the minimum value of lambda and omega. Also, we solve here the given problem for tilde of k greater than 0 and tilde of k less than 0 respectively. When tilde of k is greater than 0, the desired solution is equal to gamma sub 1 plus alpha S sub gamma sub 0 over eta times e raised to the quantity of beta sub 1 plus alpha S sub k over eta times the quantity of t minus t sub 0 and gamma sub 3 minus alpha R sub gamma sub 0 over eta times e raised to beta sub 3 minus alpha R sub k over eta times the quantity of t minus t sub 0. When tilde of k is less than 0, the desired solution is written on this form.
The sixth statement of the problem, the derivation of model for population growth leads to a differential equation. In population growth model, we assume that rate of population is proportional to current population. That is, the derivative of x with respect to t is equal to kx is a current population. K is proportionally constant, represents growth rate. For population of bacteria, we cannot say at certain time amount of bacteria is exactly 10 or 20. It can be measured approximately. That is, initially number of bacteria is approximately 20. So this approximate number can be represented using fuzzy number. In solution of growth model, we cannot get exact amount of population. The appropriate growth model is described using fuzzy concept. The growth model problem is stated as a culture initially has about n sub 0 numbers of bacteria. The rate of growth is proportional to the number of bacteria present. The constant proportionality is k. Given this, in case 1, we got the answer quantity of 3 times 10 raised to 6 plus 2.5 times 10 raised to 6 alpha times e raised to 0.4055 t. For n sub 2 t alpha, we use the general form below. We got the quantity 7 times 10 raised to 6 minus 2.5 times 10 raised to 6 alpha times e raised to 0.4055. For the decay problem, a very important physical-chemical parameter of water is the concentration of dissolved oxygen necessary for all living aquatic organisms. In this paper, we numerically illustrated a fuzzy model to describe the decay of the dissolved oxygen concentration in water using the solution of first-order linear homogeneous fuzzy ordinary differential equation.
In this paper, the researchers have considered first-order linear homogeneous fuzzy ordinary differential equation where fuzzy number is taken as GTFN. Its solution procedure is described in 3 cases. 2 biomathematical models are numerically illustrated as its applications. Hence, the researchers conclude the following. Number 1. A fuzzy number is a convex, normalized fuzzy set where membership function is at least segmentally continuous and has function values at least one element. There are special types of fuzzy numbers named after their shapes, but the triangular fuzzy number is the most common one. Also, operations on fuzzy number can be generalized from that of alpha-cut interval. Number 2. A generalized fuzzy number is called generalized triangular fuzzy number if it is defined by tilde of A is equal to A sub 1, A sub 2, A sub 3, omega. Its membership function is given by this piecewise function, or in this form. Number 3. Given the first-order linear homogeneous ordinary differential equation, derivative of x with respect to t is equal to kx with initial condition x of t sub 0 is equal to x sub 0, This ODE is called fold if any of the following three cases holds. First, only the initial condition is a generalized fuzzy number. Second, only k is a generalized fuzzy number. Third, both k and x of 0 are generalized fuzzy numbers. 4. Given the first-order linear homogeneous ordinary differential equation, derivative of x with respect to t is equal to kx with initial condition x of t sub 0 is equal to x sub 0, x sub 1 of t alpha is less than or equal to x sub 2 t alpha for all alpha element of the interval 0 omega, where omega is greater than 0 but less than or equal to 1. Then tilde of x of t is called strong solution. Otherwise, it is weak. Number 5. The solutions generated from solving fold in type 1, type 2, and type 3 are all generalized fuzzy numbers. 6. The solution of first-order linear homogeneous fuzzy ordinary differential equation can be used to numerically illustrate biomathematical growth and decay model, specifically like the rate of growth in culture of bacteria and rate of decay biochemical oxygen demand.
That's all, and thank